Okay, let's unpack this. Today, we're diving into a really fundamental concept in computer science and, well, problem solving generally: dynamic programming.
Yeah, DP. It's one of those terms that can sound a bit intimidating at first.
Right, it sounds complex, but the core idea behind it is actually surprisingly elegant and really powerful once you see it in action.
Definitely. Think of it as a smart strategy for tackling problems that might seem, overwhelming or just way too slow to solve directly.
And to help us really get a handle on it, we're using a great resource today, Section 14.1 from Hello Algo on dynamic programming. They do a nice job starting with basics.
They really do. So our mission, if you will, in this deep dive is to properly understand what dynamic programming is, how it actually works, and crucially, why it's so effective.
Yeah, why it makes such a difference.
And we'll use a classic example they provide to walk through it all.
So, at its heart, dynamic programming is about breaking a big problem into smaller pieces, which, okay, that sounds like a lot of problem-solving techniques.
It does, but here's the key thing, the DP twist, as you called it earlier. It's specifically designed for problems where those smaller pieces, those subproblems, overlap.
Overlap, meaning you end up needing to solve the same small problem multiple times if you're not careful.
Precisely. And the genius of DP is making sure you don't do that. You solve each small piece just once, remember the answer, and then reuse that answer whenever that same piece crops up again.
So it's about efficiency, avoiding redundant work.
Exactly that. And this smart reuse is what turns some problems that seem exponentially hard, taking forever with brute force, into problems solvable much, much faster, often in polynomial time. It's a huge leap.
Okay, I think we need that example to really see this.
Agreed. Let's use the one from the source. The climbing stairs problem. It's very accessible, but illustrates the core ideas beautifully.
Climbing stairs. Okay, what's the setup?
Imagine a staircase with, say, n steps. You're standing at the bottom, maybe step 0,
Right.
aiming for the top, step n.
Right.
The rule is simple. With each move, you can climb either 1 step or 2 steps. That's it.
Okay, 1 or 2 steps at a time.
And the question isn't about speed or the minimum number of moves. It's how many different ways, how many distinct sequences of 1s and 2s can you use to land exactly on the step?
Ah, okay. So counting the unique paths. Let's try a small one, like the source mentions. 3 steps. How many ways to get to step 3?
Right. Well, you could go 1, 1. That's one sequence.
Okay, 1 way.
Or you could go 1, then 2.
That's 2 ways.
Or you could go 2, then 1.
3 ways, is that?
That seems to be it. Just those 3 distinct sequences. And the source confirms, yes, 3 ways for these.
That's simple enough for 3 steps. But I can see how this would get complicated fast if you had like 10 steps or 100 steps. Listing them all out would be a nightmare.
Absolutely. We need a more systematic approach.
So what's the first thought? Usually it's something like, try everything. Brute force.
Yeah, that's often the most intuitive starting point. You can think of it as exploring a tree of possibilities. At each step you're on, you have a choice. Go up 1 or go up 2.
Branching out.
Right. You follow every possible path downwards, or upwards in this case. If a path lands exactly on step n, you count it. You could implement this using, say, recursion or backtracking.
Explore all paths, basically.
But there's another way to think about breaking this down, maybe more formally. Let's define something. Let's say d pi is the number of ways to reach step I. This d pi represents our problem for step I.
Okay, d pi is the answer for step I.
Right, and d pi 1, d pi 2, those are the answers for the smaller subproblems. Now think about how you could possibly arrive at step I.
Well, following the rules, you could only have come from step I1 by taking a 1-step jump, or you could have come from step I2 by taking a 2-step jump.
Exactly. Those are the only 2 possibilities for the very last move that landed you on step I.
Ah. So the total number of ways to get to step I must just be the number of ways to get to I1 plus the number of ways to get to I2.
You got it. That's the crucial relationship. d pi I equals d pi 1 plus dp2. This is the heart of it. It's what we call the state transition equation. It connects the problem to its immediate subproblems.
Okay, that looks familiar, like the Fibonacci sequence almost.
It's very similar in
Yeah,
structure, yes. Now, a purely recursive brute force approach could just use this formula directly. To find dpn, it calls the function for dpn1 and dpn2.
And those calls then call functions for smaller steps.
Recursively breaking it down until they hit the simplest cases, the base cases.
What are the base cases here? The start of the staircase.
Kind of. The smallest problems we know the answer to directly. How many ways to reach step 1?
Just one way. Take a single 1 step. So dp1 equals 1.
Right. And how many ways to reach step 2?
You could do 1 plus 1 or just 2, so 2 ways. dp2 equals 2.
Perfect. Those are our initial states, dp11 and dpt22. The recursion stops when it hits these known values.
Okay, so the recursion works its way down from dpn to dp1 and dtn2. But hang on, when you calculate dpn, you need dpn1 and dpn2. But then, to calculate dpn1, you need dpn2 and dpn3. Look, dpn2 just got requested again.
Exactly. That's the critical observation.
It seems like you'd be calculating the same values, like dpn2 or dp5 or whatever, over and over again in different parts of the recursion.
You absolutely would. If you draw out the recursion calls, like the tree diagram in the source material, you see the same subproblems appearing in multiple branches. This is the classic issue of overlapping subproblems.
And that's why brute force recursion is slow. All that repeated calculation.
That's precisely the problem. Each calculation might be quick, but you end up doing an exponential number of them. The time complexity turns out to be which grows incredibly fast. For even moderately large n, like 40 or 50 steps, this becomes completely impractical.
Okay, so brute force is out for anything non-trivial. The overlapping subproblems kill it. So how do we fix that? The obvious idea is, well, if you calculate something, maybe write it down. Don't calculate it again.
Exactly. Don't recalculate. Remember the results. And this leads directly to the first optimization technique, memo-wide search, or simply memoization.
Memoization, like writing a memo to yourself.
Pretty much. The idea is straightforward. Use some kind of storage, like an array or a map, let's call it mem, when your recursive function needs to calculate, say, dpi.
First, check the storage.
Yeah. First, look at memi. Is there already an answer stored there? If yes, great, just return that value immediately. No more recursion needed for this branch.
Okay, and if not?
If memi is empty or marked as not yet computed, then you proceed with the recursive calculation. dpi calculate dpi1 plus calculate dpi2.
And those recursive calls will also use the memoization logic.
Correct. And crucially, before your function returns the newly computed value for dpi, it stores that value in memi.
So the next time anyone asks for dpi, the answer is ready and waiting.
That's the essence of it. It's often called a top-down approach because you start the calculation from the top problem, dpn, and use recursion to go down, but you fill your memo table as you compute results on the way back up or across the recursion tree.
Right, the recursion structure is still there, but the memo table acts like a cache.
It does. And as the source materials diagram shows, this dramatically prunes the recursion tree. Any branch asking for a subproblem that's already been solved is cut short immediately with a quick lookup.
So each unique subproblem, like dp5 or dp10, only gets fully calculated once.
Exactly once, the first time it's needed.
And what does this do to the performance, the time complexity?
It's a game changer. Since there are only distinct subproblems, dp1 through dpn, and each one is now computed just once, the total time complexity drops to linear.
Wow, from exponential down to linear, that's huge.
It's the difference between waiting seconds versus potentially years for larger n.
Okay, so memoization is top-down recursion plus caching. Now, you also mentioned dynamic programming, often described as bottom-up. How is that different?
It achieves the same result solving each subproblem once, but it approaches it from the opposite direction. Instead of starting at dpn and recurring down, standard dynamic programming starts with the smallest, simplest subproblems, the base cases, and works its way up.
Bottom up, so it calculates dp1, then dp2, then dp3, and so on in order.
Exactly. It typically uses iteration like loops instead of recursion. You set up an array, let's properly call it the dp table now, maybe dpeppable, of size n plus 1.
Okay.
First, you initialize it with the solutions to the initial states. dpeople1 and dpeople2 equals 2.
Fill in what you already know.
Right. Then you iterate, usually with a loop, say for I from 3 up to n. Inside the loop, you apply the state transition equation, dp plus dp1 plus dp2.
But crucially, when you calculate dpi, the values dp9 and dp22 are already in the table because you computed them in previous iterations of the loop.
Precisely. The bottom-up order guarantees that when you need the solutions to subproblems, they are ready and waiting for you in the table. You just look them up.
So you just fill the table step by step. dp3 uses dp1 and dp2. Then dp4 uses the just calculated dp3 and the known dp2. Keep going until you fill dpn.
Yep. dp3 becomes 2 plus 1 equals 3. dp4 becomes 3 plus 2 equals 5. dp5 becomes 5 plus 3 equals 8, and so on, until you reach the last cell, dpn, which holds the final answer.
This feels very methodical, very direct, no recursion overhead.
It is. It's purely iterative. And because it also calculates each DP value exactly once, the time complexity is also just like the memoized version.
Okay, so memoization, top-down recursive with cache, and DP, bottom-up iterative with table, both get us to time by solving overlapping subproblems efficiently. They're just two different implementation styles for the same core idea.
That's a great way to put it. Two sides of the same coin, really. Both rely on identifying the state, like step I, the state transition equation, d pi bi plus d pi 2, and the initial states, dp11, dp22. The DP table is explicit in the bottom-up approach and implicit, the memo cache, in the top-down one.
Okay, time is fantastic. But both approaches seem to need storage. The DP table needs an array of size n, and the memoization cache also stores results for up to n subproblems. So the space complexity is too.
Yes, for the standard implementations we've discussed, the space complexity is indeed to store the solutions to all the subproblems from 1 to n.
Is that always necessary? Can we do better on space?
That's a very sharp question.
Okay.
And in this specific problem, yes, we can. Look closely at that state transition again, d pi I equals dp1 plus dpi2.
Okay.
To calculate the number of ways for the current step I, which previous result do you actually need?
Well, just dpi1 and dpi. The ones immediately before it.
Exactly. You don't need dpi3 or dpi4 or anything earlier to calculate dpi. Once you've used dpi2 to find dpi, you won't need dpi2 again for any future steps.
Ah, I see. So we don't actually need to store the entire history in the table.
Not for this problem. Since we only need the results from the two preceding steps, we can optimize the space dramatically.
How? Instead of an array?
Instead of an array of size n, we only need to keep track of the latest two values. We can use just two variables.
Like one variable for dpi1 and one for dpi2.
Precisely. Let's call them priv1 for the value at I1 and priv2 for the value at I2. When we iterate to calculate the value for the current step I, let's call it current, it's simply current priv1 plus pri2.
Okay, that gives us the answer for step I, but then we need to prepare for the next step, I plus 1.
Right. For step I plus 1, the value we just called priv1, which was dpi1, will become the new priv-a. And the value we just calculated, current, which is dpi, will become the new priv1.
It's like they shuffle along. The old priv1 becomes the new pri2, the current becomes the new priv1.
Exactly. It's like a little sliding window holding just the two values you need. You initialize priv2 for dp1 and priv1 for dp2, and then loop from I3 to n, calculating current priv1 plus priv, and then updating priv to p2 and priv1 its current.
Wow. Okay, so you're still doing the calculations, but you're only ever storing two numbers, essentially.
Plus the current one maybe, so a constant amount of space. The space complexity drops from down to 1.
That's impressive. Constant space. Does this optimization technique have a name?
It's often referred to as using a rolling variable or rolling array approach, or sometimes space-optimized DP. It's applicable whenever the current state only depends on a fixed small number of previous states.
So to recap this whole journey, we started with simple recursion, the brute force way.
Which was intuitive, but terribly slow, because it kept recalculating overlapping subproblems.
Then memoization came to the rescue. Top-down recursion, but with a cache or memo table to store results and avoid recalculations. That got us to time, but still used space.
Right. Then we looked at the bottom-up dynamic programming approach, using iteration and a DP table to build the solution from the base cases upwards. Also, time and space.
And finally, for this specific problem, because the transition only needed the last two steps, we could optimize the DP approach to use only space using those rolling variables. Still time.
That summarizes it perfectly.
The fundamental idea, then, that defines dynamic programming is really about identifying that overlap in subproblems and exploiting it, either by remembering results top-down or building them iteratively bottom-up.
Yes, that's the core insight. Decompose the problem, recognize the overlapping subproblems, find the relationship, the state transition, handle the base cases, and then solve efficiently by storing and reusing subsolutions.
This climbing stairs example, while simple, really does lay out all those key components clearly. State, transition, initial states, DP table, and even space optimization.
It's a great pedagogical example for that reason. It provides a solid foundation, and this pattern of thinking applies far beyond just stairs.
Right. Connecting this to the bigger picture, where else does this DP thinking apply?
Oh, countless areas. Algorithm design classics like the knapsack problem, finding the longest common subsequence between two strings, used in file comparison and bioinformatics. Shortest path algorithms in graphs, like Floyd-Warshall, optimizing decisions over time in finance or operations research.
So basically, anytime you have a problem that seems breakable into smaller, similar problems, and you get a nagging feeling you might be solving the same small problem repeatedly within the larger calculation.
That's exactly when a little light bulb should go off. Maybe dynamic programming could work here. Identifying that potential is the first step.
It really makes you think. Now that you've seen how DP elegantly solves this stair problem, how it moves from that slow brute force to a really efficient method, maybe take a moment to consider problems you encounter, perhaps in coding or puzzles or even strategic thinking. Where might you see this structure of overlapping subproblems where remembering past results could be the key? Recognizing those situations is where the real power of understanding DP lies.